Title of this presentation is Investigations of an Encircling Pulse Eddy Current for Corrosion Detection. This work is a collaboration between Brunel University in London and TWI Ltd in Cambridge. In this presentation, I'm going to give you a brief introduction about NDT and the motivation for this work and the proposed pulse eddy current probe, and then finite element analysis of the pulse eddy current and experimental setup. I will show you some results and then the conclusion. Non-destructive testing, as the name suggests, is the process to evaluate the properties of a material without causing damage to it. This is a very important area in the industry because it saves a lot of time and money in inspection of the different systems and equipment while they're in service, or they can be shut down for a temporary period of time. There are various inspection techniques that are already known and are used widely in industry. In visual testing, which is the first and oldest inspection technique and is still being used a lot in industry. Ultrasonic testing has been widely used over the past decades. Long-range ultrasonic or guided wave testing over the past 20 years, there has been a lot of research done in this area. Radiographic testing methods are still being used, but because of the safety problems, they are not widely used in industry at the moment. And eddy current testing and other electromagnetic techniques are very much used for finding localized cracks and corrosions. And eddy current testing has been used for aerospace, transportation, and food industry a lot. Motivation for this work was that over 1 million kilometers of pipelines carry hazardous fluid in Europe, and most of these pipelines are thermally insulated to be recovered from the environmental damages that can happen to them. But this, when the water gets trapped between the insulation and the pipe, damage occurs in terms of the corrosion, local corrosion, and can cause devastating failures if not inspected and treated in time. Different inspection techniques are available, one of which is pulse eddy current technique, which was proposed in the past 30 years. In this slide, I'm going to give you a quick introduction about eddy current itself. It's electromagnetic. Eddy current, like any other electromagnetic technique, is a non-contact technique, so it can be used for detection over insulation because it doesn't need to be in contact with the material. And it employs a coil and takes advantage of electromagnetic induction. Conventional eddy current probes use AC current, sinusoidal AC current, which carries one frequency for inspection, which arises one of the limitation of the eddy current, which is the depth of penetration. By definition, depth of penetration is a standard depth of penetration is a depth at which eddy currents reach 37% of their density from on the surface. And in applications, about 2 depth of penetration is detectable. But this depth of penetration does not only depend on this equation, which is dependent to the frequency of the driver coil, to the permeability of the magnetic permeability of the material on the test, and the electrical conductivity of the material on the test. It also depends on the probe itself and the size, the thickness of the material under inspection. So pulse eddy current technique was proposed to use a broadband, to use a pulse for exciting the coil, which uses a broadband, which has a broadband frequency spectrum, so that the more depth of penetration can be detected in one scan. So this is the general overview of the systems available. The one on the right shows the existing pulse eddy current probes. This type of probes are called surface probes or pancake probes. They have different configurations. They use different windings and different core materials, but all of them sit on top of the pipe, and it's assumed that the cross-section of the pipe is much larger than the cross-section of the coil, so that the pipe wall can be assumed as a plate state in compared to the cross-section of the coil. What we have proposed is an encircling pulse eddy current probe. So it's basically a very simple wire going around the outside the circumference of the pipe, and so that the whole circumference can be inspected in one scan. So to understand this phenomenon, we use finite element analysis using COMSOL Multiphysics. We took advantage of AC/DC module of COMSOL, and we used the multi-turn coil for our coil, which the model assumes a current carrying region for the coil and solves for the magnetic vector potential and finds the magnetic field. And then we use the time-dependent study. As you can see, there is a 50 millimeter gap between the pipe and the probe and the coil, which was assumed which was there to simulate the non-conductive insulation. So this one shows the 3D model of the encircling pulse eddy current probe around the coil. So that's the coil, and then you can see the magnetic flux on the pipe, and when there is a defect simulated in the pipe, the magnetic flux is disturbed, and you can see the higher flux around the edges of the defect. For this paper, we had one pipe available with 3 manufactured defects on them, and you can see the description of the defects. Defect A has the highest depth of 7 millimeters, and wall thickness of the pipe was 40 millimeters. And I just showed one of the results of the simulation for defect A. There were 4 sensors assumed around the coil. They are from 90 degrees from each other, and the sensor 1 is assumed to be in the center of the corrosion, and looking from the top to the center of the corrosion, and the other 3 are avoiding the corrosion. But since the eddy currents travel around the pipe, all the 4 sensors are disturbed by the presence of this defect, and you can see that it can be detected from the other 3 sensors as well. And the overall system description for the experimental setup is that we have a driver coil which excites the coil with a pulse excitation. Then we have the magnetic field sensors, and they are connected to the signal conditioning circuit, which is then connected to the data acquisition card, and a computer with Matlab on it for data analysis and visualization. And this is the experimental setup that we use in the lab. If you can see, we have made the 3D, we have made the coil former using a 3D printer, and then it's clamped on a wooden wheels to be able to move it on the pipe, and it can be opened and closed. This coil can be used for bigger diameter pipes, but then the insulation will be assumed less than 50 millimeters. And this one is the schematics of the coil, and then the 4 GMR sensors are placed inside the coil former. And these are the experimental results for defect A. And in this result, also the sensor is placed in the center of the corrosion, and you can see that the one that was in the center of the corrosion has the highest amplitude, and the other 3 have less. But they can still detect the corrosion. So I didn't show you the results for the other 2 defects. These are only the extracted features from those results, as you can just the amplitude of the signals from model and the experiments, and you can see they are in good correlation. There is about 0.4 millivolts differences in some of the cases, like defect C. But if you and then the other thing that has to be noted, that defect C has a higher amplitude in compared to defect A, which was the highest depth. That's because these defects, detections are directional as well. So if you look here, defect A is in the circumference of the pipe, and this one is longitudinal. And this type of probe is more sensitive to the longitudinal defects. So since more eddy currents will be disturbed by a longer defect. Yeah, I think I am very quick. So in this presentation, I showed you we employed finite element analysis period in this work to find the best place for the sensors and also to find the best number of windings for the coil we made, which was made after we designed the driver circuit. And then discontinuities were modeled for different magnetic fields. And then, I didn't tell you this, sorry. These signals are differential signals. If you notice, there are differential signals because the absolute signal of a defect and a non-defect signals are very similar. So to increase the resolution, we subtract the defect signal from a reference signal. Then the reference signal is taken from a non-defective pipe, so it's like a calibration for the system. And then you take away the defect signal from a reference signal to find the differential signals. Otherwise, the signals are very similar and can't be distinguished between the two. Future work is the modeling and experimental investigation of wall thinning under insulation and cladding. If you remember, I spoke about these pipes being thermally insulated, and they usually have a covering of metal covering the insulation, which is very challenging for eddy current. We have done simulation and experimental for 3 different covering materials of stainless steel, galvanized steel, and aluminium. And the results for that work is submitted to NDT Evaluation Journal. And the modeling and experimental investigation of corrosion under insulation and cladding needs to be done, but computationally are very expensive, so we are working on that. And then the other thing, we have to increase the number of sensors. As you mentioned, I mentioned that we have the sensor on top of the corrosion. So if all the sensors are avoiding the corrosion, then it won't be possible, we won't be able to find the location of the corrosion. We can detect there is one corrosion or there is a disturbance to the pipe in that circumference, but we can't say where exactly it is. To increase number of sensors can help locating the corrosion inside the pipe as well. Okay, thank you for your attention.